So I request Dr. Biswajit Das, please start the session. Recording has been started.
Okay, sir. Okay. Uh, and many people are joining. Okay, we can start now. Good evening, everyone. So today, indeed, auspicious day, as we celebrating today is a Maghi Purnima, where the full moon graced the sky in all the radius, and this is symbolize the enthusiasm, prosperity, and harmony. So it is a perfect occasion to grace here in pursuing of knowledge, learning, and collaboration. So it is my great pleasure to welcome you all to this AICT sponsored 6-day online faculty development program under the AICT Teaching and Learning ATAL program. The title of this program is Advances in Material Science for Sustainable Development and Industrial Applications, organized by Department of Basic Science and Humanities, Dr. Sudhir Chandra Sur, Institute of Technology and Sports Complex. So we sincerely appreciate the participants' enthusiasm, engagement, and valuable uh, participation over the past few days. Uh, and today we have two insightful sessions. Session 5, uh, topic is green chemistry, given by Dr. Abhijit Kundu, Senior Director, TCG Life Science. And session 6, topic is tailored polymer nanoparticles for targeting cancer drug delivery, given by Professor Dr. Dibakar Dhara, Senior Professor in Material Science, Department of Chemistry, IIT Kharagpur. So with this small introduction, so now I may request that Dr. Dipankar Das, HOD, Department of Basic Science and Humanities. So please, sir, come on this platform and introduce our first honorable esteemed speaker, Dr. Abhijit Kundu, Senior Director, TCG Life Science.
Okay, thank you, sir. Good evening, all. Respected Honorable Speaker, sir, Dr. Abhijit Kundu, sir, and also respected participants. Now, I'd like to read out the short biodata of Dr. Abhijit Kundu. So, am I audible?
Yeah.
Am I audible?
Yes.
Am I audible?
Yeah.
Okay, thank you.
Yes, you are audible.
Okay, thank you. So, Dr. Abhijit Kundu is a distinguished chemist and Senior Director, Chemistry at TCG Life Science Private Limited. He has an extensive background in organic and organometallic chemistry, with over 2 decades of research and leadership experience in both academia and industry. Dr. Kundu completed his BSc and MSc in chemistry from Jadavpur University, followed by a PhD in 1996 to 2000 from the Indian Institute of Chemical Technology, IICT, Hyderabad, under the supervision of Professor Sujit Roy. His doctoral research focused on a novel copper-2 tin to reagent and its applications in organometallic reactivity and in situ spectroscopic diagnostics. He pursued postdoctoral research at Western Michigan University, USA, 2000 to 2001, working with Dr. Brian Buffin on the synthesis of potentially chelating nitrogen ligands and their water-soluble complexes of palladium and platinum, exploring their catalytic applications in aqueous media. Subsequently, he joined UT Southeastern Medical Center, Dallas, Texas, 2001 to 2003 as a postdoctoral researcher under Professor J. Falak, where he worked on chromium-mediated organ synthesis. He joined TCG Life Science Private Limited in 2003 and has been an integral part of science, contributing significantly in drug discovery, medical chemistry, and injection research. Currently at TCG Life Science. So thank you. So over to Dr. Abhijit Kundu, sir. So go ahead, sir.
Yeah, so can you see my screen?
You are presenting?
No,
Yeah, your screen is visible, sir.
Can you see my screen or?
Yeah, your screen is visible.
Okay. Thank you for the kind introduction, and thank you for giving me the opportunity for this lecture session. So I'm going to present green chemistry today, and before going into the main topic, I'll talk about the impact of chemistry on our everyday life, and also the idea or the reason why this concept of green chemistry came on. So please feel free to stop me at any point of time. Should you have any question, I'll be happy to answer. So my first slide is
Sir, sorry for interruption. Your slide is not visible.
can you see now?
No, sir.
Not yet, sir.
Just yeah, I'm sure now it should be fine.
Yeah, absolutely fine.
Yeah, so the title of my first slide is Chemistry and Society. So we all know that chemistry is essential for meeting our basic needs like food, clothing, shelter, health, energy, and clean air, water, and soil. And we also know that chemical technologies enrich our quality of life in numerous ways by providing the new solution to the problems in health, materials, and energy usage. And here I have just captured few things which will highlight the tremendous impact of chemistry in our life. And the first one is pharmaceutical, where where we make drug molecules for different kind of disease. Next is agriculture, which deals with the production of fertilizer and pesticides. For food industry, we are manufacturing preservatives, packaging, food wraps, and refrigerants. In the medical industry, they are used for disinfectants, vaccines, dental fillings, anesthetics, and contraceptives. Transportation also, it is significantly used for production of petrol and diesel, and also catalytic converters to reduce the exhaust emissions. For clothing, synthetic fibers, dyes, waterproofing materials. For safety, they are used as polycarbonate materials, which are used for crash helmets. In sports industry, it is used as composite materials for rackets. In office use, this is used as inks and photocopying toners. And at homes, these are used just for example like paints, varnishes and polish, detergents and pest killer. In my next slide, I'm going to show you some examples of very important chemical disaster incident that happened across the globe at defined period of time. So the first one that I have captured here is in 1956. This was Minamata disease, and it was first discovered in the Minamata city in Japan. And the cause for this disease was release of methyl mercury in the industrial wastewater from one of the chemical factories. In 1961, another disease came up, which is called Itai, that was caused by cadmium poisoning due to the mining in Toyama Prefecture in Japan. In 1976, the Seveso disaster was an industrial accident that occurred in a small chemical manufacturing plant near Milan in Italy. And this resulted in the highest known exposure of TCDD, which is the short form of 2378 tetrachloro-dibenzopidioxine. And it is very harmful and carcinogenic. Next one is in 1984, and probably we all are aware of this incident in Bhopal in MP. This was due to the release of methyl isocyanate, which is a very highly toxic gas, and that resulted in the exposure of over 500,000 people, and many people died. Next, in 1986, the Chernobyl disaster was a nuclear accident at the Chernobyl nuclear plant in Ukraine. That also resulted in a severe release of radioactive materials, and there have been many fatalities from the accident due to the radiation poisoning. And in 1989, Exxon Valdez, that was an oil tanker that hit a reef and that spilled an estimate amount of 10.8 million US gallon of crude oil. And it has been recorded as one of the largest spill in the United States history and one of the largest ecological disasters. So from this example, what I would like to highlight is that the impact of the hazardous chemical. So in order to maintain a sustainable environment, we need to have a control on the use of this hazardous compound. So before that, we need to know which is hazardous and which is not. So from this, the concept of green chemistry slowly evolved. And in 1990, the Pollution Prevention Act, that was first came up in the United States of America. And this act, this helped taking some initiative towards dealing with the pollution of these hazardous materials. And it actually paved the way to the green chemistry concept. Next, in 1998, Professor Paul Anastas and Professor John Warner, they introduced the term green chemistry. And they also developed the 12 principles of green chemistry, which I will explain in one of my later slides. And further, I will also elaborate each of those with case studies. And in 2005, Professor Noyeri, he identified 3 key developments in green chemistry. One is use of supercritical carbon dioxide as a green solvent, aqueous hydrogen peroxide for clean oxidations, and also the use of hydrogen in the asymmetric synthesis. And all these 3 development they are still having significant use in the overall organic synthetic chemistry. Now, if someone asks, what is meant by green chemistry? So green chemistry or sustainable or environmentally benign chemistry, this is the design of chemical products and processes that reduce or eliminate the use and generation of hazardous substances. And also, from a chemical perspective, this green chemistry actually applies to all the different type of chemistry like organic chemistry, inorganic chemistry, biochemistry, analytical chemistry, and also the physical chemistry. Next, I will explain the 12 principles of green chemistry, and also I'd like to emphasize on this slide. This is a very important slide because all these points, all these principles, they are all the pillars of green chemistry. So if one needs to understand what is green chemistry, they first should understand what these terms mean. So the first is waste prevention, and this means it is better to prevent the waste than to treat or clean up waste after it is formed. It means that we have been doing reaction where we are, along with the desired compound, we are also ending up with some side products, and then we are finding some ways how to separate those side products which are hazardous, and sometimes also they are very carcinogenic. So in the green chemistry principle, this one says that we need to plan the reaction in such a way, we need to design the reaction in such a way that my byproduct will not form. Next is atom economy. By atom economy, it says that synthetic methods that should be designed to maximize the incorporation of all the materials used in the process into the final product. So all these points I will elaborate in my subsequent slides with particular case studies. So I'm not going to explain all this in details. Third principle is less hazardous chemical synthesis. This means wherever practicable, synthetic methodologies that should be designed to use and generate substances that possess little or no toxicity to the human health and the environment. Fourth point, designing safer chemicals. What does it implicate? Chemical products that should be designed to preserve efficacy of function, but at the same time, it will reduce the toxicity. Next point, point number 5, safer solvents and auxiliaries. So we have to design our reaction in such a way so that use of solvent and auxiliary substances that should be made either unnecessary wherever possible, and if they are used, they should be non-harmful. Next is design for energy efficiency. This means energy requirements that should be recognized for their environmental and economic impacts, and those should be minimized. Synthetic methods that should be conducted, always we should have the aim to conduct them at room temperature and also under normal pressure. Next point number 7, principle number 7, that is use of renewable feedstocks. This means a raw material or feedstock that should be renewable rather than depleting whenever technically and economically practicable. What does it mean? Because as of today's date, many of our starting material, they come from either petrol or diesel. But we know that we have a limited stock of those things. So from the green chemistry view, what we need to do, we need to reduce those resources which are coming from non-renewable source, and we have to use more of the sourcing material which are coming from renewable feedstocks. Next is reduce derivatives. So we have to plan a reaction in such a way that there should be less number of steps and there should be less number of deprotection and protection in the synthetic steps. Number 8 is catalysis. This means we should use a catalysis to reduce the energy which is required for the reaction that I am planning and improve the selectivity. Next is design for degradation. This means we have to design the chemical products in such a way to break down into harmless substances after their use. Real-time analysis for pollution prevention. This means analytical methodologies that need to be further developed to allow for real-time in-process monitoring and control prior to the formation of the hazardous substance. So this means when I'm carrying out a reaction during the synthesis only, I should know whether the side product, the byproduct, or the harmful substances are being formed or not, and accordingly we can take a decision whether to stop the reaction or whether we need to continue. The last principle is inherently safer chemistry for accident prevention. This means we should plan our reaction with substances and the form of the substances, those are used in a chemical process, those should be chosen to minimize the potential for chemical accident, including release, explosion, and fires. So after I have explained all these principles, now I'll explain this figure that is on the right hand side. So here we can see that at the center of this figure, this is called PAS. So here this P corresponds to prevention, A corresponds to assurance, and S corresponds to sustainability. So as you can see that all these 12 principles, they have been segregated into 3 circles. And for the pink circle, you can see this is under pollution and accident prevention. So in this category, we have number 1 principle, waste prevention, number 3, less hazardous chemical synthesis, and number 8, reduce derivative. In the blue one, which is called safety and security assurance, number 4, 11, and 12. And in the yellow circle, this is under the energy and resource sustainability. We have number 2, 6, and 7. These 3 principles are there. And you can see that there is one number 5, which is overlap between both the pink and the blue. So that means it can come under both the safety and security assurance and also under pollution and accident prevention. And number 10, which is designed for degradation, it comes under both of these pink and the yellow circle. And for the principle number 9 is catalysis, that is overlapping between the safety and security assurance and also the energy and resource sustainability. Now, when we are dealing with green chemistry, we also need to understand what is meant by economic barriers. So economic barrier in green chemistry that refers to the financial challenges that companies face when they are attempting to adapt the green technologies. Because sometimes when we are buying new instruments or we are implementing new technologies, those involves significant amount of cost, and we are uncertain about the outcome, whether those are going to help or not. And also we have a tendency to continue with the existing things. So this economic barrier means that is a kind of financial barrier that that one face when trying to implement this green chemistry. Moving to slide number 6. So in this slide, what I'm showing or what I'm highlighting is these principles, what they address and how. So these principles address the toxicity. And how it addresses the toxicity? It can address the toxicity by reducing the hazardous substances. It also addresses the feedstocks, and it can be achieved by using the renewable resources. It also addresses designing safer products. How? By designing non-toxic products. It also addresses biodegradability, and this can be achieved by enhancing the breaking down at the end of the life of our desired product. It also addresses energy by reducing the energy needs. For accidents, it can be achieved by proper planning. It also addresses the efficiency, which can be achieved by planning, shorter process, and synthesis. Moving to the next slide, and here I have captured few points which highlight how the current trend, I mean, how things are being done now, and what we should do in future. So at present, most of the industries, they are geared toward cleaning up after the wasteful chemical synthesis. So all their synthesis, those involve most of the time formation of their desired product along with some side product. So once it is formed, then they plan to clean up those side product and hazardous substances. Today's scientific literature is filled with synthetic pathways which are inefficient in terms of design. And also, when we are selecting the reagents for a particular reaction, those are seldom selected with regard to hazard. I mean, we do not consider the hazardness of those reagents or starting material that much. And also, industrial chemicals, they do not have minimal hazard as a performance criterion. At the same time, there persist a significant number of chemicals in the biosphere and in our bodies, which are a major global health issue. And at present, a vast majority of the organic chemicals, they are made by depleting the non-renewable feedstocks, which the green chemistry does not support. Also, our chemical industry deals with the safety through engineering and security through the barricades. But from the green chemistry, we get the idea that we should plan in such a way to prevent the accident. Next slide, here I'm going to highlight about the benefits of green chemistry. So the environment, how it can benefit from green chemistry. So as I already mentioned that we will design our products in such a way those will biodegrade and won't persist in the environment after their lifetime. For human health, we have to make products, or we should plan making the products those does not make any toxicity for the humans and all the living beings. The economy, how it can benefit, because if we can make novel products using the green chemistry, that may boost the competitiveness. For sustainability, what we already mentioned, that we have to design the products which can be made from renewable resources. And for science, this how science can get benefited is by some new ideas where we can create new IPs. Next, I would like to talk about the Presidential Green Chemistry Challenge Award. And this award was started in the year 1995. And this award program enables individuals, groups, or organizations to compete for annual presidential rank awards, which recognize innovation in cleaner, cheaper, and smarter chemistry. And by highlighting them, by highlighting these outstanding technologies which incorporate principles of green chemistry into their chemical design, manufacture, and use, this awards program actually better enables the industry to meet its pollution prevention goal. And here I have captured one example. Professor Lipsuch is from University of California, Santa Barbara. He is the recipient of this award in the year 2011. So the project that he got, objective of the project was towards ending our dependence on organic solvents. Now we know that still today, most of the chemical manufacturing industry, they heavily depend on organic solvents. And most of the time, these organic solvents, they tend to be volatile, toxic, and flammable. And many times, they are hazardous, they are carcinogenic, they are less boiling. And after the reaction, once the reaction is complete and we isolate our desired product, those solvents, they become waste. And it needs a huge investment and huge effort to treat those waste. Now, what we can do here? So, at one time it was thought that if water can be used as a replacement of organic solvents. But the main problem is that most of the organic compounds, they do not dissolve in water. So we have to mix the water with something which will help solubilize the organic compound. So here, Professor Lipsuch, he designed a safe surfactant which forms a tiny droplets in water, which is nothing but a micelle type molecule. And organic chemicals, they dissolve in these droplets and they react efficiently, which allows water to be used as a solvent and as a replacement of organic solvents. And this particular surfactant is called as TPGS 750M. This is a designer surfactant, and it is composed of safe, inexpensive ingredients like tocophenol, vitamin E, succinic acid, methoxypolyethylene glycol, which is a common degradable hydrophilic group, also called MPG 750. Now, this TPGS 750M, this micelle, this forms nanomicelles in water that are lipophilic on the inside and the hydrophilic on the outside. So this organic reaction, this take place in this lipophilic part, which is inside of the micellar molecule. Now, what we found that using this new micelle in water, a lot of reaction can be done. And here I have just captured few of them, which are like ruthenium catalyzed olefin metathesis, which is also known as Gauss metathesis, and I'm sure many of you are aware of this term. Name reaction, pyridine catalyzed cross coupling like Suzuki, Heck, Sonogashira, unsymmetrical aminations, allylic aminations and silylations, aryl borylations, pyridine catalyzed aromatic carbon hydrogen bond activation to make new carbon-carbon bonds. Now, in a nutshell, this technology offers opportunities for industrial processes to replace larger amounts of organic solvents with very small amounts of a benign surfactant nano-dispersed in water only. And over the years, this has been used by many academic labs, many industries, many biotech companies. And due to its significant impact, this award was given to him. So my next couple of slides that highlights that some of the solvent selection tool, those have been developed by big pharma companies. So here I have one, and this has been developed by Pfizer company. So here you can see there are three different columns. One is preferred, one is usable, and one is undesirable. Now, if you look at the list of undesirable, most of the solvents like dichloroethane, dichloromethane, diethyl ether, dimethyl formamide, N-methyl pyridine, pyridine, dimethyl sulfate, and dimethyl. So all these solvents are still being used in significant amount. But green chemistry says that we need to replace all these solvents. And the one mentioned under the preferred column, water, acetone, ethanol, 2-propanol, 1-propanol, ethyl acetate, isopropyl acetate, methanol, methyl ethyl ketone, all these are preferred. So if we have any opportunity of using this instead of this, that is always advisable. And under the usable column, if there is no option of using this due to the nature of the reaction, we can look into this option. If nothing works, then only we'll come to this. Next is the solvent development tool by GSK company. Here also the ones in the greener area, those are advisable to use. The one in the yellow, these are kind of mixed issues. If we do not have anything from this list, then we can select something from here. But these under the area which is highlighted in red, these are completely restricted as per the green chemistry principle. But as all of us know that many of these solvents are still in use. Next is another slide on safer solvents and auxiliaries. And here, this is another guidance from Amgen company, where they have developed it, and in our organization, we have used it, and we found that this works absolutely fine as a replacement of dichloromethane. Because dichloromethane is a solvent which we use quite often during purification of organic compounds on silica column. So Amgen has developed a guide to replace this dichloromethane with greener alternatives, because dichloromethane is known to be associated with respiratory and cardiovascular toxicity in humans, carcinogenicity, and genotoxicity. So this guide on the right, it compares the eluting power of different greener alternatives to dichloromethane. So this one is black. This one is dichloromethane in methanol. So at 1, it is 1% methanol in dichloromethane. It is 2.5% methanol in DCM, and so on. And the ones on the top, there is 3%. This is 3:1 ethyl acetate and ethanol in heptane, and this is 10%. So we have to make a mixed solvent of 3:1 ethyl acetate in ethanol, and this will be used as a percentage in heptane. And the second one is ethyl acetate in heptane. Third one is IPA in heptane. And these are ethyl acetate ethanol mixture in MTB, methyl tertiary ether. So according to this figure, if someone as of today using 2.5% methanol in DCM, so ideally he should be able to use 30% of IPA in heptane, or 65% of ethyl acetate in heptane, or around 40% of ethyl acetate ethanol 3:1 in heptane. So this is the Amgen's green solvents for chromatography in practice. If a compound suitably elutes in 5% DCM in methanol, the bar chart that predicts that 60% 3:1, because this corresponds to around 60%. 60% 3:1 ethyl acetate ethanol in heptanes, or 40% of IPA in heptanes, those should be good alternatives. So from this slide, I'm going to elaborate the 12 principles with some case studies. So the first one that I'm going to talk about is waste prevention. So according to this says that if from A plus B, these two are my starting material, I am getting P plus W, where P is my desired product and W is my side product. So it says that I have to plan my reaction in such a way so that I end up only with P and this W does not form. That's why it is explained as it is better to prevent waste than to treat or clean up waste after it is formed. So as I said, we have to plan like in such a way so that we can avoid the generation of W. And we need to find now, in order to do that, if my objective is to making this W portion 0, so I have to change A and B. So we have to find alternatives to A and B to improve the overall efficiency of a reaction. And we also need to incorporate better catalysts to push the reaction to full completion. So this one example for waste prevention, and this is for the blockbuster drug sildenafil citrate. This is also known as Viagra. This is a selective inhibitor of phosphodiesterase 5. In short form, it is known as PDE5. This new drug that immediately became a huge hit and which achieved sales of more than $1 billion in the US market. Now, with such a rapid sales, it was obviously important that its impact on the environmental that is very low. So in the original synthesis that consists of 11-step synthesis, and the overall yield was only little more than 4%. It is very, very low. This synthesis in one of its steps used tin chloride, which is a major environmental polluter. In many of the steps, the reagents have been used in stoichiometric amounts, and one example is thionyl chloride as a solvent. This also has a huge environmental impact. In one step, they also use hydrogen peroxide. This causes burns upon skin contact, and this is a fire and transportation hazard. And for 1 kg of the desired compound, that produced 1300 liters of waste. So this is shown in this figure, how the process has been improved and how it impacted the amount of waste per kg of the product. So in 1990, when this compound was first discovered and it entered the market, it produced 1300 liter of waste per kg of the desired compound, that is a drug. And here, this portion in red, that is coming from dichloromethane, which is highly toxic. And the rest amount is coming from acetone, ethanol, methanol, and many other solvents. Now, in 1994, with the improved synthesis, the amount of the waste could be reduced to 100 liter per kg, which is a significant amount of improvement. And then by another modification in 1997, it was further reduced to 22 liter per kg. And after the commercial route, it was now reduced to 7 liter per kg of the drug. And in future, the target is if we can further get it reduced to 4 liter per kg. This is the slide where I'm continuing the story about sildenafil. So for the alternate route, the average yield for last 3 steps are 97% yield, and reduction of the ratio of solvent waste per kg over 17 years, that was brought down from 1300 liter per kg to only 7 liter per kg by minimizing the solvent use, increasing solvent recovery, improving solvent selection, and telescoping steps. Only the solvents T-butanol, ethyl acetate, 2-butanone, and a trace amount of toluene still require disposal. So we can see that over the years, significant improvement is done, and we can consider in the direction of green chemistry initiative. This is the structure of the molecule, and here in this bar chart, here it is showing some different kind of waste. So for organic waste, it was for the initial period, so it was brought down significantly. For the aqueous waste, again it was brought down significantly. The same also holds true for the vapor emission. Now the second principle is atom economy. Synthetic methods should be designed to maximize the incorporation of all materials used in the process and into the final product. So what does it mean? It means that ideally all the atoms from the reagents are incorporated into a final product, because we understand that if the reaction is of high atom economy, that will produce very less amount of waste, and we don't need to treat those waste because the amount will be very less. This also implies that there are no co-products or byproducts in the reaction, and also the molecular waste is therefore reduced. Now this is one case study on the atom economy, and here the molecule is styrene. Now we know that styrene is a very important starting material because which acts as a precursor for the polystyrene, and we all know that polystyrene is one of the most widely used plastics, and it is being produced in huge scales. So in the conventional method, the procedure starts with benzene, then it reacts with ethylene to get to the ethyl benzene, and then at a very high temperature, the dehydration takes place. Now, just to highlight the two disadvantages here, benzene is a known carcinogen. So here, if we want to make a green synthesis, our objective should be to replace the benzene with other starting material. And the other disadvantage is that for this step, the temperature requirement is very high. So with these objectives, this is the alternative synthesis. And here, this molecule is obtained again in 2 steps, but using non-benzene starting material. And the reaction is a Diels-Alder reaction where the atom economy is 100%. And we are also using a catalyst system, heterogeneous catalyst, which is very easy to isolate and recycle. This is another example of atom economy. So, and this deals with the drug ibuprofen. We all are aware of this drug, which is used to treat mild to moderate pain, fever. And this was the first synthesis of ibuprofen. And we can see that this synthesis consists of total 6 number of steps. All are stoichiometric in the nature. And overall, it is less than 40% atom utilization. So since it is produced in very high scale every year, because of its importance in the treatment of to reduce the pain, so there was always one desire to get a greener synthesis, which will consist less number of steps and with a higher atom utilization. So alternatively, this synthesis came up, which just consists of 3 steps, and all the 3 are catalytic steps. And for this overall synthesis, it has 80% atom utilization. Next, the principle that I'm going to discuss is less hazardous chemical synthesis. So this means whenever practicable, synthetic methodologies that should be designed to use and generate substances that possess little or no toxicity to human health and the environment. Ideally, we should use non-toxic substances whenever we are planning to synthesize a chemical product. Now, as I said in one of my earlier slides, that for many of the organic synthesis, the reagent that we are using are still hazardous. But at the same time, due to this green chemistry initiative, many labs, many teams, many groups across the globe, they are working towards the green chemistry reactions. So as of today, we have a good number of defined types of reactions that we can explore whenever we are planning a synthesis. And to mention some of those, like multi-component reactions, one-pot reactions, CH activation, metathesis, enzymatic reactions. These are some examples which can give a very clean profile and very selective and efficient synthetic tools, and these are now available to synthetic organic chemistry. So here is a case study about synthesis of adipic acid. Now, we all know adipic acid, which is also known as hexane dioic acid. This is one of the most produced commodity chemicals worldwide, with a projected global market size of more than $7 billion by 2019. Adipic acid is a versatile building block for an array of processes in the chemical, pharmaceutical, and food industries. And its main use is a precursor for the synthesis of polyamide nylon 6,6. Now, the original synthesis, this again starts with benzene, which is a known carcinogen. This has been used as a starting material for long. This also involves, this whole synthesis process also involves oxidation with an excess of HNO3 in this step. And this reaction also produces nitrogen oxide gas, N2O, and which is a known carcinogen because it's a greenhouse gas. And this accounts for approximately 5 to 8% of worldwide anthropogenic N2 emission. So it was always a desire to get an alternative synthesis greenhouse synthesis, and this is the alternative synthesis of adipic acid. And we start with glucose, which is a very good starting material from the green chemistry perspective. So in the alternative synthesis of adipic acid, this is obtained from D-glucose, and this D-glucose is currently derived primarily from the corn starch. In this synthetic pathway, it is expressed that the bacillus coagulans ear in a Saccharomyces cerevisiae strain, producing the muconic acid. And this developed a three-stage fermentation process which enables the synthesis of adipic acid from glucose. Now, in this step, there is a biocatalytic process which uses yeast, which converts the sugar to cis muconic acid here. And this intermediate stage allows the ready access to catechol. This is called catechol and the adipic acid. This also uses water as a solvent. So this is also a greener approach in terms of the solvent use. Next principle that I'm going to talk about is design for energy efficiency. So over the years, there have been different type of technique those are developed, and these are more often used as of today, and one of them is sonochemistry. And in this sonochemistry, it uses very high frequency 20 to 100 kilohertz sound waves to promote the chemical reaction. And what it does, this collapse of bubbles formed in a solution, this generates a very high temperature and a higher pressure than conventional heating. This is used in the production of triglycerides from methyl transesterification. Next is microwave. We all know, and we have microwave at home, and today everyone is using for that. But you'll be happy to know this is also being used in the chemistry labs very efficiently, because the reactions which takes like 24 hours, those reactions, many of those reactions, not all, many of those reactions can be achieved in a very short period of time. And it uses high frequency electric field to heat or cool the local environment with electrical charge. And this also avoids unnecessarily prolonged residence time at a given temperature. Next one is the photochemistry. And we all know that due to this work, Nobel Prize was awarded. And this photochemistry also being used significantly across the globe in many labs, because we found that many of these reactions which cannot be done under normal thermal condition, those can be achieved in a very simple way using the photoredox chemistry. So this can be done naturally using the sunlight as a catalyst. This can be used also in photo-driven acylation for the production of valuable synthetic intermediates and commercial fragrance in bulk. This was used by BSF to develop automotive primer coating. This is a precursor readily able to be cross-linked under photo irradiation as opposed to its conventional energy-intensive thermally driven variation. So all these things has significant advantage over the conventional conditions which we have been using for long, and still they are being used. But along with them, these new technologies, these new protocols, these are also being used in a good number. Now, this is a case study for design for energy efficiency, and this is exemplified by the drug atorvastatin. And we all know that this is a cholesterol-lowering drug, and it's but we all know that its synthesis in the synthesis process for this compound, there are two steps where the reaction needs to be done at very low temperature, which needs to be maintained using dry ice and solvent like acetone. So it was again very much requirement to come up with some alternative by which we can avoid this use of very low temperature in the town-scale production of atorvastatin. So this is the new biocatalytic synthesis which uses enzyme DARA, and this reduces the reaction time in a very short way, and also as I said that it removes two energy intensive chemical steps which require very low temperature. Next is the principle that I'm going to talk is use of renewable feedstocks, and here the case study is for development and commercialization of toners. This is heavily used, and they are being produced in tons. So in the conventional synthesis, you know that over 400 million pounds of toner they are consumed only within the US each year. And in this conventional synthesis, these toners are obtained from the petroleum-based starting materials. So they are difficult to remove from paper, and which makes it very difficult for recycling purpose. So here objective was to come up with something where this toner can be removed and the papers can be recycled. So this is the alternative where these toners could be obtained from renewable feedstocks. So in the alternative process, the development of a novel bio-derived printer toner that is easier to de-ink so that we can remove the toner from the paper. That is the objective. And this technology incorporate functional groups in their toners which are susceptible to chemical degradation for recycling, which means those toners can be very easily removed from the papers. These toners are bio-based, derived from soybean, oil, and corn. And at the 25% market penetration, this technology, this could reduce the CO2 emissions by 360,000 tons per year. So you can see the impact of all these things. And whatever we are discussing, if we can combine everything, and you can feel that impact will be huge. Next is reducing the derivatives. So we have to plan the synthesis in such a way so that the synthesis process does not involve unnecessary derivation. Like in many syntheses, we have to protect the hydroxy or amino group. But in this approach, we should plan or design the synthesis in such a way so that we can avoid this use of protecting and deprotecting groups. And also, this also involves the temporary modification of physical and chemical processes. So those should be avoided. So here in this conventional approach, you can see the process starts here. Then we get intermediate A in step 1. Then after several steps, we are ending up with the product. As there will be more number of steps, that will involve more number and more resource of everything. So in the greener approach, what we are thinking, if we can plan the synthesis in a single steps. This is another example for reducing derivatives, and this is 6-amino penicillinic acid, which is a core moiety of penicillin. So in the conventional synthesis, this was made in 3 steps, and this also involved many hazardous reagents like silyl-based reagent and phosphorus pentachloride, which is also harmful. But in the alternate synthesis, this is achieved with an enzyme, and in a single steps. Next one that I'm going to talk about is catalysis. So this catalyst, we all know what a catalyst is. They work by lowering of the activation energy. So without the catalyst, if this is our activation energy, by using the catalyst, we can reduce the activation energy, which means that the reaction can take place at a much lower energy when I'm using a catalyst in the reaction. This also reduces the temperature significantly, and that also control the site of the reaction. That means it enhances the selectivity. So in a nutshell, catalysts are chemical compounds that increase the rate of a reaction by lowering the activation energy required to reach the transition state. Unlike reactants, a catalyst is not consumed as part of the reaction process. The process of speeding up of a reaction by using a catalyst is known as catalysis. And these are the list of different type of catalysis properties, and those are broadly classified in two categories. The one on the left is heterogeneous catalysis, and one on the right is homogeneous catalysis. Now, among the different properties for heterogeneous catalysis, there are some good advantages. Like for heterogeneous, the main advantage is it can be readily regenerated and recycled. It can be readily separated, and also it has a long service life. And for the homogeneous catalyst, among all the properties, the ones in bold, like very high rates, robust to poisons. So you cannot easily poison the homogeneous catalyst, whereas this heterogeneous catalyst can be easily poisoned. High selectivity and mild conditions. Those are among the properties of homogeneous catalyst, which has advantage. And now, if these advantages we can combine into a single catalyst, that will be called green catalyst. And our objective is to make new type of catalyst which will consist of all these properties, which is not an easy thing, but if we have proper rationale, we should be able to get to this kind of catalyst. So these are the examples for the catalysis. In the interest of time, I'm skipping this slide. And this is designed for degradation, and the case study here involves fire extinguisher. So in the conventional approaches, chemical additives or alternatives to water for firefighting applications can have negative long-term environmental and health effects. Halon gases like bromotrifluoromethane, they are destructive to the ozone layer, and aqueous film forming foams release both the toxic hydrofluoric acid and fluorocarbons when used, and fluorosurfactant compounds, they are resistant to microbial degradation, often leading to the contamination of groundwater supplies and failure of wastewater treatment system. So here is a alternative new type of fire extinguisher, and these are based on pyrocool FEA, which stands for fire extinguishing foam. So this is a foam which is non-toxic and highly biodegradable, and these two are the desired properties under green chemistry. And this has a low application volume, and extinguishing an oil tanker fire estimated to take 10 days can be put out in 12.5 minutes using this new type of fire extinguisher. This is one example for inherently safer chemistry for accident prevention. So these are picture from inside the aeroplane. So these seats, these are made of polyhydroxyamides. So these are called safe polymers because these are synthesized under mild condition, and if there's an accident, explosion or fire, this decomposes. I mean, this kind of safe polymer, they decompose into fire-resistant polybenzoxazole, which are not that toxic or carcinogenic. Next is real-time analysis for pollution prevention. And this means that analytical methodologies that need to be further developed to allow for real-time in-process monitoring and control prior to the formation of hazardous substance. So real-time analysis for a chemist is the process of checking the progress of chemical reaction as it happens. So during the reaction, we'll be able to know how far the reaction has gone, whether any side product or waste has been formed, and accordingly we can take a decision. Because when we know that our product is formed completely, then we can stop the reaction and it can save a lot of waste, time and energy. Because many times we put a reaction in the evening and we just continue it for overnight, but actually that reaction may take only 1 hour. So this analytical chemistry, so I wanted to highlight is that analytical chemistry has been at the heart of the environmental movement since its inception. It has been used in identification, monitoring, measurement, and characterization. These are some of the things, or you can say some of the initiative that we have taken at our organization. The first one is, over the years, we have observed that suppose 10 people working in one lab, 2 people, they are ordering the same compound or same reagent because they do not know that both their scheme, they need the same reagent or same starting material. But in the recent time, in the past few years, we have been monitoring the issuance of the chemicals by the chemist in a particular lab on a real-time basis. And what we have been doing, we are issuing small or lower volume or amount of the chemicals and pyrophoric hazardous stuff to the chemist as per their requirement in the project. We are encouraging continuously our people to use greener solvents and safer reagents. We also organize seminars on green chemistry time to time for people awareness. We also have stopped issuing multiple number of same chemicals, cleaning of the refrigerator where it is stored all our unstable chemicals. Those are being cleaned in regular time interval so that we do not store a single item for long time. Cleaning of unused chemicals from labs in regular time interval. We have a team which monitor all these things. We also monitor the usage of water to reduce the amount of water which is being used. Same also applies for the electricity. And last but not the least, this is my final slide where I'd like to highlight few things which needs to be done by all of us. So as we all know that this idea of green chemistry, this has been known since 1990, but the real implementation of those rules in the drug designing and synthesis has still been limited. So all of us need to advocate the application of green chemistry in the drug designing process where sustainable bio-based building blocks could be used as starting point. These building blocks, they can be produced from biomass or through a bioprocessing route, because all these bio-based starting material, they are less hazardous compared to the petroleum-based chemicals, and in most cases the products are self-degrading in the environment. There are several bio-based chemicals which can be used as starting materials for synthesis of many of the intermediates and final compounds. Those are like 1,4-diacid, like succinic acid, fumaric acid, malic acid, 2,5-furan dicarboxylic acid, aspartic acid, 3-hydroxypropionic acid, glutamic acid, glucaric acid, levulinic acid, and itaconic acid, and also 3-hydroxybutyrolactone, sorbitol, glycerol, xylitol, arabinitol. So all these alternative starting materials, they can be used to achieve the same organic compound, but for them at present we are using something different. So those can be replaced with this bio-based starting materials. So all this kind of bio-based starting material, this can offer plausible routes for producing everything from biofuels to pharmaceuticals, following the major principles of green chemistry. Another thing that we need to take care of, continuous processing, which is also known as flow chemistry. This is another acceptable approach for swift reaction times, rapid reaction screening, and optimization of operational protection. And many labs across the globe, across the world, they have started using the flow chemistry because it has many advantages. And the last one is in silico or computational approaches for drug design through machine learning and artificial intelligence. This is one very, very important factor and which can have a huge impact on green chemistry. Because if we have a good approach towards this in silico and computational approaches, we can theoretically predict that out of the 1,000 molecules, which will have good drug properties and which will not. Accordingly, we can plan our synthesis. So this will save us development of thousands of unnecessary drug synthesis and chemicals by predicting their early toxicity profiles and metabolism through this machine learning and artificial intelligence. These approaches will save time, money, reduce waste, and most importantly, this will save animal testing too. So that was my final slide. And I would like to conclude with this famous quote by Professor Paul Anastas. The general public needs to know that green chemistry is possible. Green chemistry is better chemistry. So this all bottles down to the fact that we need to increase the people awareness. And if all of us can have some role in that initiative, in that approach, I'm sure we'll be able to achieve at least some of our goals through green chemistry. So thank you for your kind attention. And if you would like to know additional information, this is my email address and phone number. So you can contact me separately if you'd like to know more information. Thank you. Any question?
Thank you. Thank you, sir. Thank you so much for your wonderful, engaging, and enlightening session through your lecture. And based on you say that the application challenges and future direction of green chemistry. In this your lecture, we have learned about the wide range of use of this chemistry in daily life, and however there are some hazardous chemicals also, and we need to be aware of that because they are sometimes cause very catastrophical disasters such as Bhopal gas tragedy. And so that then we need, that's why this is a real need to present time to focus on the green chemistry. And you have shows the development of green chemistry and over the time, and 12 guiding principles of this green chemistry: minimizing the waste, reducing toxicity, and promoting eco-friendly alternatives. And also you have mentioned that we have very much used with regularly used the organic solvents, but they have also hazardous, toxic, and continuous in creating industrial waste. So green chemistry can also be alternative used for these uh, organic solvents. And you have showcased us with multiple applications of how to synthesize this green chemistry by different techniques, and the with the beautiful case studies. And with that, and we are really thankful once again, the heartfelt thank to you, sir, for sharing this valuable insight and this uh, and inform us the future of chemistry and green chemistry towards sustainability. So thank you so much for this beautiful and wonderful session, sir. And
Thank you very much.
thank you. And now I like to request from our participants. So if you have any queries, so sir is with us. So this is an open forum for discussion. So either you can ask, unmuting you, or you may text in a chat box.
Hello, sir. I have a question.
Yeah, please.
I am Dr. Saurav Das from Dr. B.C. Engineering College, Durgapur. So my question is, this green chemistry, as you told, it is already well known from 1990. But at the present day, what is the status? Are that your medicine companies, pharmaceuticals, are they using this type of green chemistry, or still it is going on conventional way?
No. It has been used on a very high scale because because there are many things like you have to maintain certain rules in your organization. Like as our organization, when we are receiving a business, we have to show to them that we are maintaining all the safety protocols and like what is the world standard. According to that rule, we are maintaining everything. So unless you can prove to them that you are maintaining that safety standard, you will lose the business. So like that, everywhere there is an initiative. But you're absolutely right, because it's a long way to go. So that's why I said all of us need to come forward and they have to take part in this initiative. They only will be able to achieve. But I can 100% confirm that there have been many effort. And if you are really interested more, you can reach my email, or you can also reach my phone number. I can give you specific examples what we are doing exactly, or I can share with you some literature which are very recent, and we are doing the same thing. We are implementing the same thing in our organization. Not only us, everyone, all the organization. Because if they do not follow those, if they do not maintain, they will lose the business.
Thank you, sir. Sir, another question.
Yeah.
You have renewable feedstock. Can you elaborate this thing? Renewable feedstock.
Yeah. Renewable feedstock, as I said that, because as of today, still many of the starting materials, they are based on like petroleum based.
Yeah.
But you know that those stocks are limited. So if we continue to use them, so at one point of time, we won't have anything. And that is one of the reasons that why we are electrical vehicle now on the roads. Right.
Yes, sir. But
So-
there is one problem regarding electrical vehicle also. You need to charge the battery and then you have to draw the electricity from the grid. And ultimately going in the same row, in the loop.
See. We all human beings, we have a tendency to continue with the existing procedure. Whenever we try to implement any new thing, there will be a lot of resistance will come from the public and from us. Just yesterday, I was reading one article in one of the magazine. It is called Reader's Digest. In the country Norway, 80% of the vehicles are EV. I was surprised to know. And that was achieved with the sacrifice of something.
But sir, what about the charging the battery? You need electricity, no? So for that,
Yeah.
again, you have to burn the coal.
Another challenge is there. Myself, Dr. Somu Mukherjee from Metallurgical Department, Kazi Nazrul University.
Yeah, please.
For electrical vehicle, you need appropriate minerals, and lithium source, nickel source are very scarce. How we are going to process all these things for mass scale? And
Yeah.
for processing that extractive metallurgy, what you have mentioned is regarding green chemistry, that will be violated 100%.
Yeah,
That is
but
very difficult
yeah,
actually.
yeah,
Though we are approaching for bioleaching and all these things, but still it is not proven.
yeah. I said that this is at a very early stage. We all
Yeah.
are working towards that, and it will take many years. But what I'm trying to say,
There
what
is
I'm
one direction we have started.
yeah, yeah. What I'm
Another thing that I want to know from you, Dr. Kundu,
yes,
suppose we people are talking from Indian background, that is waste management and all these issues. So is it also linked with your green chemistry concept?
absolutely.
Uh,
But as I said in one of my earlier slide that as per green chemistry, the reaction should be planned in such a way that your waste is not formed. But
okay.
we know that it is easy to say, but it is difficult to execute. But the approach is like we should plan a reaction in such a way that my side product, byproduct, other waste should not form.
Okay. Another thing that I want to know is our country is focusing on semiconductor mission and all these things. Okay. Now, as per the previous day lecture, if I correctly remember, uh, making the chips, that is electronic chips. Okay, not the food audible chips. They require huge chemicals, which are some of the chemicals are quite corrosive in nature. So, how you are looking after this?
Yeah, yeah. Again, I am
But
just
we
trying.
are in the world of electronic age.
Yeah, again, I am trying to highlight that we are not aware about all the research that is currently being done across the globe. But for all these things which are very useful for the coming years, for our next generation, research is being done to replace the existing starting or existing resource. Those are hazardous. But for that, you need to read a lot about those things. So if you have any specific interest, you can get in touch with me, either my email or my phone number. I can try to help you to direct in the right way.
Okay, thank you, Dr. Kundu. Thanks for
Thank you.
your thanks for your information. Thanks.
Thank you so much.
Okay. Thank you, sir. And is there any question? Oh, okay. So with that, actually, I want to share that thank you, sir, for accepting our invitation to deliver this wonderful lecture in this AICT teaching learning program, that is faculty development program. And with that, from our side, as is because it is a digital platform, so one digital memento as a token of a small token of appreciation. Sir, I want to request that if you kindly stop your presentation so I can share that.
Can you say again? There are some.
If you kindly stop your presentation, so then I can present.
Okay. Yeah, I have stopped it.
Yeah. Thank you. And this is one small token of appreciation from the Department of Basic Science and Humanity, Dr. Sudhir Chandrashur Institute of Technology and Sports Complex. Sir, please accept this digital memento from our side.
Thank you so much for this. So if you can email a copy of
Yeah,
that.
sure.
Yeah, thank you so much. And as I said, that thank you for giving me the opportunity for this talk. I'm very glad that I could find time and make this presentation and present it here.
Yeah.
Hope we'll meet sometime again in the near future, and maybe I'll talk in another topic.
Yeah. Because this is only the starting, and we need to move more forward in better future. Green chemistry is most important, and we need your guidance, sir.
Thank you so much. Yeah.
Thank you.
Okay. So I think
Okay.
with that
Okay.
we can conclude here.
Yeah.
Because I think the next speaker is already there. We
Yeah.
can see. So,
Okay.
okay.
Okay. Good night.
Thank
Thank
you.
you, sir.
Thank you.
And welcome Professor Dr. Dibakar Dhara sir, and he is already with us. So without wasting any time, we'll go to the next session. That is day 3, session 6. So now Professor Dr. Dibakar Dhara, he is a Material Science Department of Chemistry, IIT Kharagpur. So I just before uh, and first of all welcome you sir this ATAL FDP program, and and with your busy schedule you accept our invitation, so we are honored and privileged you have with us actually.
Well, thank you. Thank you for giving this opportunity. Are you able to
Yeah,
hear me?
yeah, absolutely sir.
Okay.
And before just start sir, I know there is no need to introduce you, but this is a protocol, so I am just read your short biography to all our participants so they can understand actually better. So with your permission, may I
Please,
want to
please go ahead. Yeah.
thank you, sir. So Professor Dr. Dibakar Dhara is a renowned scientist and professor in the Department of Chemistry at the Indian Institute of Technology, Kharagpur, India. With career dedicated to advancing poly science and its biomedical application, Dr. Dhara has made groundbreaking contribution to the field of engineering polymer nanoparticles for cancer drug delivery. His innovative research addressed two critical challenges: ensuring the stability of drug or genes within nanocarriers in physiological environment, and achieving sustainable and targeted re- release at specific tumor tissues. Dr. Dhara's work focused on developing advanced polymer systems, including random block and star polymers synthesized through controlled radial polymerization. These polymers self-assembly into nanoparticles under physiological conditions and are tailored for stimuli responsive behavior such as pH, redox conditions, and ATP levels. These redox responsive and core cross-linked micellar nanocarriers based on diblock complexes have demonstrated remarkable efficiency in delivering drugs to both drug sensitive and drug resistive cancer cells. Additionally, his pH, redox, and ATP responsive cation cross-linked polymers containing disulfide and reverse boronic ester linkage offer targeted DNA delivery in environments characteristics of cancerous cells such as acidic pH surroundings. Dr. Dhara's research achievements are extensively documented in high-impact scientific journals, including Journal of Colloidal and Interface Science, ACS Applied Material Interfaces, Langmuir Biomolecular, and ACS Macro Letters. His collaborative work has advanced the understanding and development of smart drug delivery systems with particular focus on addressing drug resistant cancer cells. In addition to his research, Dr. Dhara has been recognized for his continuous to science and academics. His accolades includes awards and honors from prestigious institutions, highlight his influence in polymer chemistry and biomedical research. He has been invited to share his insight at numerous conferences and symposiums, further cementing his reputation as a thought leader in the field. Beyond his professional achievement, Dr. Dhara is committed to mentoring the next generation of scientists and forecasting innovation through collaborative research. His contribution extends to the development of innovative materials with wide range applications in medicine and industry. Dr. Dhara's pioneers' effort in polymer science and drug delivery systems continue to inspire the scientific community. His work holds the promise of transformative advances in cancer treatment, addressing one of the most prestigious challenges in modern healthcare. So now, with this short biography, I like to request Professor Dhara. So now the platform is yours. So you can.
Okay, Dr. Das, this was, thank you again. It was a quite a long introduction from your side. Anyway, the topic or the title of my presentation is Tailored Polymer Nanoparticles for Cancer Drug Delivery. And in today's presentation, I basically want to touch upon these topics which are listed here. And I don't want to go through one by one at the beginning. Anyway, I'll go through this. Now, before I come to my research, I want to spend quite a bit time to bring all the...
Just to interrupt you, sir. So
Sure.
you are in slide presentation mode?
Yes, you're not able to...
No,
Not able to
actually,
see?
we are actually only the PPT, not presentation.
Okay, let me share it one more time. Is that okay now?
Yeah, perfectly, sir.
Okay.
Thank you, sir.
So, as I was stating that I'll touch upon these topics, and I don't want to go through each individually in each of these now. So, before I go into my specific work, I just wanted to bring all the participants to kind of a want to give some basic understanding about drug delivery systems and why nanotechnology is important for cancer therapy and so on. So let me begin with giving a general introduction on drug delivery and drug delivery system. Before that, let me formally define drug. A drug is a chemical substance that produces a biological effect when administered to the living organism. Now, this is not a nutrient or essential dietary ingredients. So other than the regular nutrient and essential dietary ingredient, whatever material or chemicals we take, which produces some biological effect, we call them as drug. Now, what is necessary for drug delivery? Now, this is one drug I take every day morning in empty stomach for my mild hyperthyroidism. Now, if you look at this amount, it is about 25 microgram. Now, imagine a situation I was supposed to weigh this 25 microgram and take every day. Life would have been miserable, isn't it? So good that there is a tablet, and each tablet contains this 25 microgram of this thyroxine. The another drug one of my family members take is this. Okay. And now this is contained two drugs basically. One is levosulpiride, another is pantoprazole. Pantoprazole is actually very common. A lot of us take this for a gas problem. Now the two terms you can see, one is enteric coated and the second term is sustained release. Now what is enteric coated? Enteric coated means that this pantoprazole molecules are coated with a polymer which prevents these molecules to come and get exposed in the stomach low pH environment. But when this drug reaches in a neutral or slightly acidic, slightly basic environment of small intestine, this polymer gets degraded and the drug gets released. Okay, so that's what meant by enteric coating. And second term is sustained release. That means this drug would be released in the stomach or in the intestine in a sustained rate, so that there is no, at any point of time, there is no, very high concentration of drug reaching the system. Okay, so that's what. This is the reasons why we require these drug delivery systems, other than just taking the drug alone in the body. Okay, so basically, obviously, when you talk about prevention and treatment of diseases, drug is obviously the choice of drug is a very important factor. But the site and duration of drug delivery and the rate of drug release and the pharmacokinetic and side effect profiles also play very pivotal role in medical interventions. And for these reasons, the development of suitable dosage forms or drug delivery systems, in short DDS, is strictly required for any drug in order to allow for a safe and effective administration of drug to the patients. Now, if we look at what happens in terms of drug concentration in our blood after a oral medicine, if we have taken the oral medicine, you can see that as the drug gets absorbed in our body, the plasma concentration of that increases, drug increases, and after some time is reached at a peak, and then when the drug gets metabolized and excreted from body, concentration comes down. Okay. Now there is a minimum concentration required for the drug to be effective for the disease which it is meant for, and this is called minimum effective concentration, MEC. And not only that, there is a maximum concentration also allowable. If we take too much of medicine, then the concentration would be above this maximum tolerated concentration, MTC. Then this drug actually become a toxic rather than a curing agent. Okay, means a helpful agent. So basically, we have to maintain drug concentration in this therapeutic region to have this drug effective. Now, most of the drugs we take once or twice in a day. Now, if we take once in twice a day, so basically this drug concentration increases, and maybe after a few doses, it maintains a steady concentration in that therapeutic range till the dosage has been discontinued, drug is discontinued. Okay, so that's the requirement, that for a drug delivery system to be effective, it should be able to deliver drug in such a way that it should maintain the proper concentration of plasma concentration of the drug. Now, there are many routes. We just mentioned about oral drug delivery, but there are plenty of routes by which drug is delivered regularly, like in eye, ear, nose, tongue, by injections, intravenous injections, and several things. And this list is it doesn't end here. There are many probably available ways you can inject or input drug in the body. Now, what is bioavailability of drugs? for example, if we take oral delivery, take a drug through our mouth, then obviously it reaches stomach, and then from stomach to the intestine, and both from stomach and intestine through this gut wall, this epithelial membrane, this drug gets absorbed in the body, and through the portal veins it reaches liver. Okay, now once it reaches liver, a part of the drug actually get metabolized in the liver, and then part of the drug goes into the blood for a systemic circulation throughout the body. So basically, the amount of drug we take, part of it is actually does not get absorbed at all. It goes through excretion. Part of the drug actually gets degraded in the stomach environment because of low pH, harsh environment, presence of lots of enzymes and microbes. So basically, there could be chances of some drug getting lost, and some drug, even after absorption, get metabolized. We call this is the first pass metabolism. So basically, the amount of drug we take, the part of it actually reaches the blood, and the amount of drug we take, the fraction of the drug reaches the systemic circulation, we call bioavailability. Obviously, it is much lower than 100% for orally taken drug, but for a regular intravenous injection, it is obviously assumed that whatever drug you are injecting directly in the blood circulation, so the drug bioavailability is 100%. Now, so basically, after looking at a oral drug must be able to do all these criteria before it reaches to the blood circulation. First of all, it has to get dissolved to get absorbed in the blood through the epithelial membranes of our gut. Then it has to survive the pH of the stomach and intestine, survive the intestinal bacteria. It has to cross the membrane, epithelial membrane. It has to survive the liver metabolism, avoid active transport of bile, and so on. Okay. So after this, only this drug can be effective in our blood circulation. So once the absorption is done, it reaches blood. Part of it, if you take orally, then part of it reaches blood, and we call that fraction bioavailability. And then once it reaches blood, it's basically gets circulated throughout blood and get distributed reversibly with tissues, and then irreversibly get eliminated through by metabolism and through kidney. Okay. So in pharmacokinetics, we have these 4 steps: absorption, distribution, metabolism, and excretion, which is called ADME. Now, if you can think about anti-cancer drugs, they're, first of all, these chemotherapeutic drugs are very costly, so you cannot take it orally. That part of it get lost, okay, and part of it reaches to blood. Secondly, you can see that this drug, if you take orally, then it has to go through the gut membrane as well as through liver. And if the drug itself is very not good for, say, liver and other places, it might actually damage liver and other places. So basically, to avoid all those things, the anti-cancer drug is always injected intravenously. So basically, chemotherapy, when we talk about chemotherapy, this is mainly cancer chemotherapy. We give the drug through intravenous injections. Now, so these the processes or terminologies for final pharmacokinetics: absorption, distribution, metabolism, and excretion. Now, metabolism is a process which is basically a chemical reaction by which a drug molecules get modified, and mostly this modification is done such a way that it actually increases the water solubility, and once the water solubility increases, it is actually easier to get out through kidney filtration. So this metabolism is a process by which drug get deactivated and mostly they get functionalized and become polar or more water soluble for excretion. Okay, and obviously the drug has to get eliminated. I'll just cover in a minute. So the two terms very frequently used in pharmacy is one pharmacokinetics and second one is pharmacodynamics. So pharmacokinetics deal with the movement of the drug or what body does to the drug, means what is the entry point, what is the where it is moves and how it is get basically excreted. So these are the questions that answered in pharmacokinetics, and once the drug goes into the plasma, then the question of pharmacodynamics comes in. It basically what drugs do to the body, whether it basically the effect of drugs towards body. It's not how it enters or how it moves through the body. Okay, so basically interactions with plasma proteins and so on, and receptor and cell and all these things. Okay. Now, once we take drug has to get excreted, and there are many methods. The major mechanism is through kidneys, and basically the drugs which are freely floated in blood circulation, they get filtered in kidney membrane, and then they pass through urine. And some of the drugs actually get reabsorbed and come back to the blood circulation process. And there's another way this liver also take part is removing these drugs from the system or circulatory systems. And there are other methods which are not does not contribute that significantly, but they also take part to remove these drugs like exhalation and so on. So after just introducing these concepts of or the basics of drug delivery, we'll talk about drug delivery systems. So basically in drug deliveries, an ideal drug delivery system will ensure that the active drug is available in the site of action for the appropriate duration of time, while without displaying any side effect, basically without displaying any physiological effect itself. And the DDS should aim to provide drug concentration at the site of action and that are above the minimal concentration. Basically, you have to have the drug in that between that highest and the lowest concentration in plasma. And this basically these factors that control this drug concentration in plasma includes the route of administration, the frequency of administration, metabolism of drug, and its clearance rate, and obviously, and of course, on the dosage form, its design itself. Okay. So basically, when some doctors or clinician, the clinical practice they have to not only consider the drug, but also the drug delivery systems, so that they have to consider how the drug is getting released in the from the actual medicine is getting released in the our blood circulation. Now there are ways these release mechanisms happen, and there are these 6 basic groups are immediate release, delayed release, sustained release, control release, stimuli sensitive release, and targeted release. So basically we can have 2 classifications. One is immediate release and second one is modified. These are all modified release. So what is immediate release? That, or sometimes we call fast release, that in this type of drug release, the drug is released immediately after administration and is designed to give a fast onset of drug action. So as soon as you take, the drug should get released and it should basically gives you fast action. Sometimes that is why if you want very fast action, these drugs are used as a chewable drugs so that it can get immediate absorption to the mucous layer of mouth, and sometimes drug is taken below the tongue so that it get absorbed much faster. Second one is delayed release. It's basically a immediate release after some time. So it will have some delay. For example, when we talked about this enteric coated polymer, so basically when the tablet or the capsule which is in stomach will not release, but when it goes past the stomach and reaches small intestine, it will release and release fast. Second is sustained. Third is sustained release, or sometimes called prolonged release and extended release. In this case, drug is released over a prolonged period of time. Okay, so this drug is released slower than this immediate release, so that the therapeutic plasma levels are maintained over a prolonged period of time, typically 8 to 12 hours. And the last one in this list is controlled release. In this case, the drug is released in a predetermined rate. So basically, in this case, you can control the release of the drug for a prolonged period of time. So it is somewhat similar to this sustained release. In fact, sometimes it is very difficult to differentiate between sustained release and controlled release. So sometimes nowadays they are actually used interchangeably. So this is the normal this plasma concentration after you take a medicine. So after the absorption, the plasma concentration goes up and then comes down. In case of delayed release, the same thing happened, but only after a certain delay. So this is the time when there is no release. Whereas in case of sustained release or controlled release, it gets released for a longer duration. Okay, and for control use, you can actually control what would be the concentration of the drug in plasma. So this basically gives you the understanding what is different between immediate release, a delayed release, and a sustained or controlled release. So basically, as I was telling, that in practice it is often difficult to clearly differentiate between a sustained release and controlled release delivery system. And so basically sometimes they are used interchangeably. These are examples of some entering coating polymers which are used for delayed release. So basically the capsule, where these capsules are made of this type of polymers and drug is kept inside. You can see these polymers have a charged ionizable side groups like COH, mostly COH in this case, because they will have a pH dependent solubility in water. So basically at lower pH, when this will remain as COH group at acidic pH, so the solubility will be less, so it will not degrade or dissolve. But when the pH is high, about 7 or more than 7, then this will become COH, CO minus. As a result, these polymers will get solubilized and the drug will come out. Okay, so that's the mechanism by which these enteric coating polymers actually work. The other things, how this sustained release or control release work, actually you have in the capsule, you have these small beads, okay, and this beads contains drug and there's a polymer coating on top of that. Now the length or thickness of the coatings are different in these small spheres. So some are having small thickness and some are having more thickness, the polymer layer thickness. So the ones which are having a thinner layer, they will dissolve faster and bring the drug out in the medium, and those spheres which have a thicker polymer layer, it will take more time, and then the drug will get delivered at a later time. So by this way, you can actually have a different thickness of polymer layer, and then by which you can control or prolong the release of the drug in the system. Okay. So there are some commercial applications, and then nowadays there are some synthetic polymers are getting used. I'm not going in detail through that. Now, after talking about this drug delivery basics and different drug delivery systems, let me bring why this nanotechnology is important for cancer therapy. Now, most of us know what is nanotechnology. Basically, nanoscience and nanotechnology are a multidisciplinary scientific field that deals with preparation, processing, and application of materials, device, system that are nanometer scale. Okay, nanometer scale means we are talking about 1 to 100 nanometer. Now, nanomaterials are materials that have at least one dimension in nanometer scale. So basically, you can have a quantum dot or carbon dot where all the three dimensions are in nanometer scale, or you can have a nanowire, you can have a nanoflake. So basically, at least one of the dimension has to be nano scale domain. That means it has to have a dimension between 1 nanometer to 100 nanometer. Now, for our drug delivery applications, this 100 nanometer may not be a strict criteria. We can go still little above this 100 nanometer, maybe 200 nanometer, and so on. There are many examples of nanomaterials and their applications. Some are and their relative dimensions. Like if you compare different geometries here, different object and their size, and then just to have this nanotechnology is deals with 1 nanometer to 100 nanometer, and there is just example of some dimensions just to have some idea about how this. Now, why nanotechnology in drug delivery? What's the utility? That's the question we need to answer. Now, if we inject a drug intravenously, so that obviously it doesn't need to go through those absorption through gut and fast pass mechanism, fast pass metabolism in liver and so on. So it can avoid those things and get the drug can be introduced in the blood itself intravenously. Now the problem is that drug is considered as a foreign material for our body. Now if some foreign body comes, there is a immune system which is called reticuloendothelial system, or sometimes called mononuclear phagocytic system. What happened because of this system, when drug comes, or for that matter, any foreign materials comes, what happens? First thing happened that protein gets absorbed on top of this. Okay, and after they get absorbed, this complex of protein actually forms a corona over this foreign body, and then once it forms, then by this phagocytic mechanism, they are taken out of body. And only if you just remember, I mentioned before also that protein-bound drugs are not active. Only the unbound free drugs, they are only available for distribution to the tissues and then underdoing their work, their activity, only unbound. So basically, what happens if you have a free drug, then part of the drug is actually gets removed from the body because of this RES system. So how can you stop? You can have drug incorporated in nanoparticles, where these nanoparticles have these polymer chains hanging around. Now, because of these chains hanging on the surface of the sphere, it actually can sterically prevent the absorption of protein on this. Similarly, you can have a charged nanoparticle like liposomes or micelles, where because of the presence of this charge, the protein absorption gets limited. Similarly, you can have also polymeric nanoparticles, where the polymer chains are, the surface chemistry are different, which basically prevent the protein absorption. And similarly, hydrogels, which are very hydrophilic surface, they also prevent this protein absorption. So basically, using these nano systems, you can actually avoid this removal of the drug from the system by this RES system or MPS system. Not only that, you can also protect the drug from the enzymes presence in the blood. So you can actually incorporate it, the drug inside this. If you have a hydrophobic drug, you can incorporate here or here. Or if you have a hydrophilic drug, then you can incorporate in this liposome inside or in this polymeric hydrogel. Or sometimes there are mesoporous nanoparticles, inorganic nanoparticles, where you can actually load or encapsulate drug. So basically, by this way, you are doing two things. One, you are actually preventing protein absorption on the surface of these particles, so that these particles do not get removed from the blood circulation. So basically, they are long circulating particles. And second, you can actually protect, and sometimes you can, this blood is a hydrophilic or water aqueous system. So the blood will not dissolve any hydrophobic drug molecules, and most of our drugs are hydrophobic in nature. So by using this type of nano systems, you can actually use this as a nano container and actually help this drug to be circulating throughout the blood, systemic circulation. Second thing is that, especially for a cancer delivery, in a traditional treatment, like in a free drug, now drug has a very small size. So beside the problem of getting removed through RES system or through kidney filtration, whatever left over, they will go into the cancer cells as well as they will go to the healthy cells or normal cells. So basically, they will do damage or kill cancer cell as well as the non-cancerous cells also. So that is the reason why this chemotherapy gives you a lot of side effects, and the patients with undergoing chemotherapy, they actually lose this hair and their immunity systems comes down drastically, and a lot of side effects happen because these drugs not only kills the cancerous cell, but it also kills the healthy or normal non-cancerous cells also, because there is no distinction mechanism by which drug cannot enter. Like they can enter only cancer cell, but they cannot enter this non-cancerous cell. Whereas if you increase the size of this particle containing drug, like the nanoparticles which we discussed in the last slide, say about 100 nanometer size, then what happened? This cancerous cell, they have a much leaky vasculature, that which means that their blood vessels are much more leaky in nature, in the sense that their porosity is much more. I'll come to the next slide to explain that fact. Now, for that, what happens? These nanoparticles, which is having, say, about 100 nanometer, they can enter in the cancer cell, but because of their large size, about 100 nanometer, they will not enter in the non-cancerous cell. So as a result, they will kill, if the drug gets released properly and get internalized in the cell. If the drug do its function, then the cancer cells will get killed and the non-cancerous cell will survive like that. So you can reduce the side effect drastically by using this non-cancer, this nanotechnology. So basically, size does matter. So ideally, for a nano system, for drug delivery system, there has to be at least 50 nanometer, and maybe the upper cut is maybe around 200 nanometer. So basically, this term, this EPR, this enhanced permeation and retention effect, that actually helps these nanosystems to stay for longer, penetrate and stay longer in cancerous cell, not in normal healthy cells. That's because these molecules with this nanosystem, they tend to accumulate in tumor tissues more than normal tissues. The reason is that, as I was stating in the last slide, that the tumors are nothing but cancerous, nothing but where there is uncontrolled amplification of the cells. Okay, so basically, whatever the cell division we normally happens, the cell division in this case happens much faster, and for that there is a great oxygen demand for those cells, because the oxygen is the food for them. So basically, they have to get this oxygen much faster rate, and for that they also generate blood vessels very fast. And as a result, the blood vessels which produce, they're structurally abnormal and contain pores, which allows the nanoscale molecules to penetrate much more compared to normal cells. And once this any drug or any molecules enter in the cells, there is another system works, which is lymphatic system, which actually takes the drug or any foreign material out of the cell. Okay. Now, for cancer cell, actually, this lymphatic system doesn't also function properly. As a result, there's the retain. These nano systems get retained in the cancer cell for longer duration. So basically, that's why this term is often used. It's called enhanced permeability and retention in cancer cells. Okay. There's another way, one concept is passive and active targeting. So whatever we're discussing about passive targeting till now, where because of the leaky nature of the cancer cell, these nanosystems containing anti-cancer drug, they goes in, whereas in healthy cells, it doesn't come in. But this can be improved further, but if we actually can introduce some surface functional groups which are having receptor, which are complementary to receptor present on the cancer cell surface. So basically, in that case, this receptor actually can tag this functional group present on the surface of these nanoparticles, and then they can actively absorb or internalize this nanoparticle inside these tissues. So in this case, you are actually using a chemical affinity between one functional group at the nanoparticle surface and at the cancerous cell surface to have a improved penetration of this nanoparticle inside the cancerous tissue. So that's we call active targeting. So basically, just to summarize in this, what is the need for this nanomedicines in cancer therapy? Because even if we inject intravenously this anti-cancer drug, these are the disadvantage we discussed, because it can get cleared by kidney, it can be cleared by the RES system, the enzymes present in the blood can degrade, and it can get in every cells or non-specific uptake. It can go to cancer cell and normal cells, causing lots of side effects. So basically, that gives us lots of low bioactivity and side effect. Whereas if we have this drug in a nanosystems, then it of a optimal size, then there are a lot of advantage we can improve. It can actually prevent this MPS system removing from this blood circulation. Kidney cannot filter this out because of kidney pores are about 6 to 7 nanometers. So if you have about 100 nanometer or 80 nanometer, the kidney cannot filter these things out. So basically, this will circulate for a longer duration, and so that the longer it basically circulates, the chances of getting these particles in the cancerous cells are more. So basically, lots of advantages, and you can have targeting ability as well. Not only that, in addition to therapeutic drugs, you can also have some agents which can actually which can actually use as a diagnostics purpose. So they can actually find out which is the cancerous cells or tissues. Not only that, if you are doing chemotherapy using this nanosystem, whether the drug is getting released or not, that can be also be followed by using another drug, another agents or diagnostic agents. Basically, it's not only this nanosystem can as a therapeutic agent, but also can be used as a diagnostics agent as well. So in combined, we sometimes use the word theranostics, where basically it's a combination of therapy and diagnostics. So nanomedicine is a much better option than free drug delivery. Now I just move to closer. I'm going closer to my topic of research, where we're talking about polymers as a nanoparticles. And if any of you are not familiar with polymers, just briefly, that polymers are made from small molecules. They're joined to make a large molecules. For example, you have ethylene monomer here, and then it get connected and make long chain, which is we call polymer. And they're mainly organic based compounds. And you can have not only one molecule, you can have multiple molecules from which you can basically combine 2-3 molecules and make copolymers. So, and these molecules can be arranged either randomly. In this case, it is arranged randomly. Sorry, in this case, it's alternatively arranged, red, green, red, green. So we call this alternating copolymer. In this case, it is randomly arranged. So we call random. And in this case, the two polymers chains are like two blocks, one green block, one red block. So we call them block copolymer. Now, you also know, probably you have studied, if you have not studied, you have not chemistry background, but if you have a chemical engineer or some other engineering background, you probably have studied this in your class 12. Then all our the soaps and detergents and all these things, we have a micelle concept, where basically if you have an amphiphilic molecule, which means a molecule which has a hydrophilic part and a lipophilic part or hydrophobic part, then when you add this in water, above certain concentration of this molecule in water, they form these self-aggregated structures, which we call micelles. Okay. Now, micelles need not to be always spherical, and this in nature, they could be different shapes also, like it could be a spherical, it could be a cylindrical, it could be a vesicular, where you have and these molecules are arranged in this way. You have a inside water pool and the outside water. They can be bilayer and so on. Now, this picture is, the cartoon is shown with a surfactant, small molecule, where you have a head group, hydrophilic group, and hydrophobic group, in this case, this tail. But you can have this same thing, same micelle formation from a block copolymer, where you can have two blocks, where one block is hydrophilic in nature and the other block is hydrophobic in nature. Now, if you have such kind of block copolymer, then what will happen? They will basically do a self-aggregated nanoparticle. They'll form self-assembled nanoparticle in water. Okay, and you can use that for your drug carrier and delivery. Okay. So basically, these are, you can have a self-assembled nanoparticles from amphiphilic molecules. Okay, now I just moved to the research from about, I have taken half of the time. So basically another half, maybe I'll just talk about my research. So, and this is some examples of our research on tailored nanoparticles for cancer delivery. Okay. Now, I'll just avoid this chemistry aspect, in the sense synthetic, how do we do the synthesis of these molecules? How do we make these polymers? How these characterize these polymers? These are done in the background. So you can take my word for that. Okay. Now, for example, we have this block copolymer here. Because of these hydrophilic groups, this block is hydrophilic and this block is hydrophobic. Okay, so actually we have a block copolymer containing one hydrophobic part and one hydrophilic part. Now, in this hydrophobic part, you have an amine group. Now, you can know that these amine groups, if you have a low pH and acidic environment, it will stay as a NH3 plus. It is charged. Now, once it is charged, it will become, the hydrophobicity will comes down because of presence of charge. And at higher pH, maybe in pH 7.2 or 7.4, which is the physiological pH, this will remain as NH2, so the hydrophobicity will increase. So now in the block copolymer, you can tune this hydrophobicity of one of the block simply by changing the pH. Now, once you change the pH, what happened? I avoided the logic, but anyway, you just understand that by just changing the hydrophobicity of this one block, you can actually change the area or volume of this chain, and as a result, the type of nanostructure or nanoparticle it form will change. Let me show you this. Before that, how to confirm that they actually form a self-assembled nanoparticle. So you can do a spectroscopic measurements. For example, in this case, we have done fluorescence measurements where we have taken a hydrophobic drug. So basically, when the hydrophobic drug are present in aqueous medium, the dye do not give any fluorescence. But once the micelle forms, the dye gets into the micellar core, hydrophobic core, and as a result, the fluorescence increases drastically. So basically, from this difference in the fluorescence, you can actually get the concentration at which this micelle formation takes place. Okay, you can see this because of this change in pH. We at pH 4.2, this is charged, so it is less hydrophobic. So that is why you require more. This is pH 4.3, you require more polymer to, because it is less hydrophobic, the tendency of micelle formation is less. So basically you require more amount of these polymers to make micelles, okay? Now, just going to the picture of these two nanosystems. Basically, at 7.4, it forms a vesicles. So inside is water, outside is water, and this is the region where it is hydrophobic. So if you taking this system, you can actually dissolve a hydrophilic drug inside and a hydrophobic drug in this membrane, this vesicular membrane. Similarly, at pH 4.2, it forms micelle. So basically, just changing the slight pH, you can change the structure from the same polymer. One is a vesicle and one is the micelle. So here you can incorporate or encapsulate hydrophobic drug. Now, why is we talking about pH? Because if you look at the difference between a cancerous tissue or cancerous cell with normal cells, in addition to this leaky vasculature, which basically helps us to helps the passive incorporation of these nanoparticles in the cancerous tissues. There are other differences, like in the cancerous tissue at the beginning, in the extracellular regions, the pH is about 6.8, and then in the intracellular region, that means within the cancerous cell, the pH is even lower, very acidic, okay, compared to a normal tissue, which is about 7.4. Similarly, this is the reducing agent, glutathione. Their concentration is much different. In a cancer cell, the concentration is much higher than normal cell. Similarly, there are other reactive oxygen species, ATP, and all this. So we can take advantage of this difference and then use this to our advantage to release the drug specifically within the cancer cell or tissues, not in normal cell. Okay. So this is another system I just want to mention where we had made this block copolymer again, and in this case, these aldehyde groups were used, one of a few of the aldehyde groups used to attach an anti-cancer drug, doxorubicin. Okay. Now, this is covalently linked, so this will not work till it gets detached from this polymer. Okay. So that is what we call product. So this is not the drug, but once it gets detached from this polymer, this drug, doxorubicin, will get released and they will become drug. They'll actually gain the drug activity. Now, once we dissolve this polymer or the product in aqueous medium, you can see it forms a very peculiar bicontinuous structure. Basically, it's a sphere. It's a spherical nanoparticle about say 100 nanometer or 80 nanometer diameter, but it has two regions, continuously two regions, one hydrophobic regions and one hydrophobic region. So basically, you can take advantage of that. You can actually incorporate both hydrophilic drug and hydrophobic drugs in here. And also we have already one drug attached to that. Now this bond is pH sensitive. So normal pH at 7.4, this will not cleave. So even if it gets entered in normal cell, this drug will not get released. So there will be no side effect. But if it goes inside the cancerous cell, then this drug, because of the lower pH, this bond will break and this drug will come out. Okay. Now, this is the result where you can see that this is the release of drug, in the sense doxorubicin, which was attached with the polymer at normal pH 7.4. You see, hardly there was any release of drug from the polymer. And when you have lower pH, the cancerous cell pH, intracellular pH, and also this presence of this glutathione in a higher extent, the drug get released much higher extent and much faster. You can actually have an additional hydrophobic dye molecule as a proof of concept. You can load, and then you can show that it also, the hydrophilic dye also get released in this cancerous environment in a larger extent than a normal cell. We have done this toxicity study, and we found that this drug is effective towards cancerous cells. So it basically kills cancerous cell, but it's not harmful to the normal cell. So this HEK293T is a normal cell, healthy cell, and MCF is a breast cancer cell. So basically, it actually kills the cancerous cell, but not the normal cell. Now, this is the difference. You can actually see. So this is the data. The left-hand side, both the data are with a normal cell, healthy cell. Okay, and the drug amount is same. This is a free drug, and this is the same amount of drug which was incorporated in this nanoparticle. Now, this blue is for a dye, DAPI, which stains the nucleus of cell. And this red fluorescence is from doxorubicin molecule. And this is using another dye, which basically stains some fibers, actin fibers, which are near to the cell membrane. So basically, it gives you the shape of the cell. Okay, it just periphery of it basically stains the periphery, near the periphery of the cells. So you can see that when you use a free drug, this is normal cell, not a cancerous cell, healthy cell. You can see with time, the doxorubicin drug actually entered in a significant extent, and as a result, they will cause lots of side effects. They will kill the normal cell as well. Whereas if you hide that drug in a nanosystem like this, you can see there is no release of doxorubicin within the normal cell. So basically, either they have not gone in, it shows that they have not gone in the normal, or it basically, in this case, it's not a it is a cell culture medium, so it is use cell culture medium, so it has not released any doxorubicin in normal cell. Similarly, when we do the same thing for a cancerous cell, now you can see is doxorubicin is coming out, but in this case, you can see that doxorubicin, because of the lower pH, they get that bond, the bond which was stitching doxorubicin molecule with the polymer molecule, they get clipped, and the doxorubicin gets slowly released. So here, it's more controlled release of the drug, doxorubicin, but whereas free drug, it's a more drastic release. So basically, that gives the advantage this actually effectively gives more anti-cancer effect than this. Okay, so that we can get from IC50 value data. So in this case, we made this block copolymer, which made this bicontinuous system, and on lower pH, it basically swells, and even lower pH, it basically degrades and releases the doxorubicin, which actually acts as an anti-cancer drug in cancerous cell. Now we have taken further this system. We have made, because if you recall the structure, it was having aldehyde group. Now, and also this has, these polymers have lots of thiol groups in present. Now, thiols are good for complexing with metal nanoparticles like gold nanoparticles. And plus, because of this aldehyde groups present, they can actually act as a reducing agent and form gold nanoparticles from this gold chloride solution. Not only that, if we make gold nanoparticles inside this, using those nanoparticles which we formed, the bicontinuous nanoparticles which showed earlier, then we can see that it's forming something like raspberry-like nanoconjugate, where you can see this type of structure, where these nanoparticles, the polymers are on the surface of this gold nanoparticle. And here you can see this gold nanoparticle and doxorubicin molecules, they are close to each other. Now, if they're close to each other, I'm not going in detail. What happens if their fluorescence spectra and the absorption spectra of either of the two, if they overlap, then one can act as a donor of energy, excited state energy, to the other. So in simple terms, basically they can talk to each other, and one can pass their energy, higher energy, to the other. So basically, what does it mean? That when we use doxorubicin, we have seen that doxorubicin gives red fluorescence color in the previous slide. But if gold nanoparticles are present close to it, then that energy which doxorubicin was used to give fluorescence, they get transferred to the gold nanoparticle, so there is no fluorescence. So basically, this method is called nanoparticle surface energy transfer. So once again, if this gold nanoparticle and doxorubicin molecules, they stay close to each other, then there will be no doxorubicin fluorescence seen. Okay. So basically, this is the curve shows that you can see the fluorescence intensity of the nanoparticle. They are very high. Now, once you are using this doxorubicin containing polymer for making nanoparticle, slowly the doxorubicin fluorescence is coming down. Okay, which means that when the doxorubicin is very close to the gold nanoparticle, their fluorescence is becoming off. Okay. Now, what's the use? The use is that you can use this distance dependent fluorescence. So what happens when this doxorubicin and gold nanoparticles are nearby? Dox fluorescence will be off. You will not see the red color. But if the polymer gets degraded and doxorubicin get released, then there will be a higher distance between the gold nanoparticle and the dox, and you will see the dox red fluorescence. So that's what happens. So in a normal cell, this is for the normal cell, you will see this nanoparticle, there is no dox fluorescence because the pH is 7.4. So dox, the particle is intact. So dox and gold nanoparticles stay nearby. So dox fluorescence is not there. Whereas in cancerous cell, because the pH is low, so the particles get swelled and degraded, dox molecule gets released. And once dox molecule gets released, the distance between DOX and gold nanoparticle increases, and we get back the fluorescence. So as you can see, that more and more DOX molecules getting released, and you can get more actually DOX fluorescence. So it shows that with time, DOX is getting released, and they are actually, now you can follow this drop. It is, you can see the March picture where this is getting released in cytoplasm and then slowly moving towards nucleus. So basically, this actually drug works by intercalating with the DNA molecule, and by which it stops the this cell division. So basically, if it is reaches nucleus, then that means it will work as an anti-cancer drug. So that's what is happening. So not only this, this particle not only basically gives you the capability to deliver drug selectively in cancerous cell, but also this gives you the ability to follow the delivery of doxorubicin in real time. So you can actually monitor the delivery of drug. Now we talked about micelles. Now what happened in micelle case, there is a potential problem, because when we define the micelle formation, we have seen that there is a minimum concentration of these amplifiers required, above which it forms micelles. Okay. Now, if you inject this micellar system in blood, and if your concentration of the effective concentration becomes dilute, then these micelles might break and release the drug which is inside that micelle. Okay. So basically, if you have a micelle like this, and if you have incorporated drug, if by chance on injecting intravenously, if the concentration becomes lower than the aggregation concentration, then it will get disassembled, and the drug will be released in the blood itself before reaching the cancerous cell. So that will cause lots of harm to the body. So to stop that, what can be done? That you can stitch this micelle. Chemically, we can stitch chemically this micelle so that it will not break. Even if that concentration comes down, it will not break. So even if the concentration comes down, it will stay as nanoparticle. Now that will not serve the purpose, because when you're stitching, you also basically entrapping the drug molecule inside. So even if it goes inside the cancerous cell, then drug will not come out. So somehow you have to cut this stitch and make this particle dissolve so that the drug get released. Now, so basically we can take advantages of this stimulus. Basically, we can see the difference. We can take the advantage of the difference between those pH and other redox environment in blood cell and cancerous cell to basically break these stitchings inside cancer cell, not in during circulation or not in normal cells. Okay. So cross-linking will provide the stability in the circulation, and stimuli responsive pre-cross-linking will provide the release inside the cancer cell. So I'll just quickly go through a couple of examples. So in this case, this is a lipoic acid containing polymer. Now this is, so basically it forms a micelle which looks like this. So basically this is a hydrophobic environment. So these groups will stay inside the core of the micelle. So the structure will look like this. So these groups will be inside the hydrophobic environment. Now, there is also some glutathione presence in blood. Now that will be good enough to reduce this disulfide bond making SH. Okay. Now, once this form SH, then there could be a linking between two SH, one from here, one from here. So there could be a cross-linking in this case. So this molecule, when you dissolve in buffer physiological pH, it will form a micelle. And then in presence of a blood fluid or in blood, because of presence of small amount of glutathione, it will become cross-linked. Okay. So that's what we observed, that when you have small amount of glutathione in what is available, what is the concentration in blood, because of cross-linking, you can actually stabilize the size. So basically, if it was not uncross-linked, so this is from a uncross-linked micelle. So if you dilute, it will come from 100 nanometer to say 5 nanometer, which means the micelles has broken if it is not cross-linked. But if it is cross-linked, even if you dilute the concentration, if you add more water, the size of the particle remains same. That means this particle is stable in against dilution as well. You can see these pictures also that they are same in nature. So it is stable against dilution. And when you have a higher concentration of GSH, it slowly swells and get degraded. You can see these particles is slowly degrading with time. So you have starting is somewhere here, and slowly this cross-linking is getting basically degraded, and the particle is swelling. And so whatever is entrapped, whatever drug, anti-cancer drug you have used, they will slowly come out from here. And that will happen exclusively or selectively in cancerous environment where the GSH concentration is much higher compared to normal cell or normal blood. So basically, cross-linking remains in normal environment and decross-linking in cancerous environment. And that is been shown in the data where this is the IC50 data. IC50 data is the means that it is the concentration of the drug which is required to kill 50% of the cells, cancerous cells in this case. So lower is the value, the more effective is the drug. So you can see these are the three polymer formulations. So free drug, this is a normal cancer cell, and this is a drug-resistant cancer cell. So you can see free doxorubicin is the anti-cancer drug. The values are 3 and 14 or 15 respectively, but where you are using this same amount of drug in a nanoparticle environment, this number comes down, especially much more in case of this drug-resistant cell. Now, what is the reason? Because the drug resistance comes because of certain burst release of this or the higher local concentration of the drug. If the concentration is higher, then there is a reflux system which takes out the drug from inside to outside. But if you release slowly, then there is not a problem. It will drug will remain in the solution within the cell, and that will have an effect. You can actually use a second drug in that nanoparticle system. Along with drug, we have loaded another one, and you can see that there is a lot of difference. So basically now it has from free drug, it is 15, it has come down to 1. It has become much more. So it is basically using this polymer nanoparticle, we can have a drug delivery in a multi-drug resistant cancer cell. I'll keep the next few slides because it's a similar concept. So I just give the final slide on those slides. But in this case, what we had earlier I showed a micellar structure. In this case, we have a vesicular structure. So in this case, using a photo radiation, we can cross-link these vesicles, vesicular bilayer. And then, so basically when it is uncross-linked, it will, and you can load this within the drug within this hydrophobic environment. So if it is uncross-linked, it releases drug prematurely, but if it is cross-linked, it holds the drug till it reaches cancer environment, and then when in presence of an acidic environment, it gets released. I'll take last 5-10 minutes to show that last example. In this case, if you recall this, what happened, the steps after you intravenously injected drug. First is circulation. The drug has to get circulate, then it has to penetrate in the tissues and then get accumulated. Once it get accumulated, it has to get internalized within the cell, and after getting internalized, drug has to get released. So basically, these are the 5 steps called CAPIR. Okay, if all the 5 steps are successful, then the drug will be effective. Okay, now, so we know that because of the leaky vasculature of the cancerous cell, the nanoparticles get accumulated in the cancerous tissues. Now, there could be 2 types of tissues in cancerous cell. One is a solid tumor, where basically the penetration is very difficult. So the drug will remain on the surface. If, say, we are using 100 nanometer, now the pore size, they could be easily entering through the blood vessel near. So it will remain on the surface, the tissues. It will not be able to enter on the inside of the cancerous tissue. So basically, it may kill the surface of the tissue, but it will not be able to kill majority of the cancerous tissues. The other thing could be a possibility that this cancerous cell or tissues may be very loose, which means even if this 100 nanometer is getting inside it will not stay there, it will come out. Okay, so first case, the penetration is a problem. The second case, this accumulation will be a problem, and as a result, internalization will be a problem. So there could be 2 problems. So what are the strategies you can use? So basically, you can have a composite nanoparticle where you have 2 size nanoparticle. So one may be 100 nanometer, another could be maybe 10 nanometer. So once this 10 nanoparticle carries the drug. So basically, once it enters in the cancerous tissue, then it will break and release this. And because now this is a smaller particles, maybe around 10 nanometer, then it can enter within this and then accumulate, penetrate, and carry the drug inside. Similarly, if the other case, you can use this same strategy, and then what happens, you can, if you can manage that, once it gets in the cancerous tissue, it will aggregate and increase the size, then it will not come out, it will stay there. Okay, so there are 2 things. For a solid tumor, you have to shrink the size, and for a loose tumor, you have to aggregate and increase the size to prevent release of this, and in this case, to increase the penetration. So I'll just quickly go through what we have done. So we have used as we have seen, that there is a slight difference in temperature between the healthy cell and cancerous cell. The normal temperature is about 37 degree, and the cancer cell's temperature is about 40 to 43. So what we have done, we have made some locopolymer, which is very, very temperature depending, very temperature sensitive to very small difference in the temperature. For example, they will remain as monomer in this low temperature, but at 37 degrees, they will form micelle. And once they form micelle, you can load this drug. Now, once these load this drug, they will stay and they can enter in the cancer tissues. Now, once they enter the cancer tissues, because of slightly higher temperature, the only 2 or 3 degree increase, we have designed the polymer such that they will aggregate and they'll become loose and they will release the drug. So they will not come out because of the size increases, but they will be able to release the drug. Okay. So I'll just, without going to the chemistry and the other things, will show you the final slide where, because I have just 2-3 minutes left. So in this case, this is a cancerous cell, and you can see that this thing works. Actually, I have skipped some slide where we have used some other techniques to monitor the real-time monitoring the release of the drops. So basically, we have used the similar strategy. When the drug is released, you will see the fluorescence of doxorubicin. So you can see that 37 degrees centigrade for normal cell, there's no release of doxorubicin, but at 40 degrees centigrade, you can see there's significant amount of release of drops. Okay, so this is free dox and this is the nanoparticle containing dox. So you can see the free dox has significantly lower amount of release than the drops present in this nanoparticle, and these drops are getting closer to the nucleus. Okay, so this basically shows that you can use this type of techniques. We are also working. I don't have time to present those. Well, this is the size aggregation strategy for loose tumor, where basically once the particles enters the tumor tissues, it will aggregate and release the drug. And because of the size increase, it will not come out. Similarly, we are also working in other strategy where we have composite nanoparticles. So once it enters the cancerous tissue, it will release smaller nanoparticles along with the drugs, and this will able to penetrate the drug in a much for solid tissue environment. So this is the what I just showed, the last one. So in this case also we are using this Fred mechanism, which I not described. So basically, using the small difference between 37 degree and 43 degree centigrade, you can actually load the anti-cancer drug in the nanoparticle system, and then using higher temperature of cancer system, you can release, and this also gives you a capability to real-time monitoring the drug. Okay, so in summary, we actually, I just showed you the importance of nanomaterials in cancer therapy and diagnostics, and I just presented some representative of stimuli responsive polymer nanostructures, which can be prepared using innovative chemistry, and you can cross-link the core of the cell of this nanoparticles to make the particles, drug-containing particles, stable during circulation, and which will get released inside the cancerous environment. You can actually tune the size for deep penetration in solid tissues, cancerous tissue, or higher retention for your loose tumor tissues. And you can use energy transfer phenomena in nanoparticles to actually real-time monitoring of the drug release. So these are some of the examples I showed you. And I want to thank my students whose work I presented in the later part. And so this is basically the work of the three research scholars. Two have been already gone out of my lab, and the one student is still working. I also want to thank my collaborator who did most of the biological studies for this system, Professor Mohitus Mondol from School of Medical Science and Technology, and for last work, Professor Malik from IIT Kolkata, and I acknowledge the funding I received from ACRB for this particular project, and then IIT Kharagpur for other assistance. Okay, thank you. And this is the picture of our old administrative building, which used to be Hijli detention camp, and it has a historic relevance. Two of our freedom fighter, Santosh Mitro and Tarakasas Sengupta, was shot dead here in one of these corridors. And Netaji Subhash Chandra Bose came here to collect their bodies. And also Mahatma Gandhi also visited this place. So I invite you, if you get chance, you come and contact me. I'll show you this facility. Okay, thank you for listening.
Uh, Firstly and foremostly, we would like to express our heartfelt gratitude to Professor Dhara for accepting our invitation and delivering such a insightful lecture in the AICT sponsored 6-day online ATAL FDP program. And in this today's lecture, we have Professor Dhara has beautifully explained the role of drugs in our daily life and how they actually work when they go inside our body, and various drug delivery mechanisms that ensure efficient treatment. The discussion covered the importance of nanotechnology in modern drug delivery system, and particularly target cancer cells actually. The session is providing in-depth analysis or the viewpoint of chemotherapy and the limitation of it, and how the nanotherapy emerging and revolution this techniques and delivery the drug delivery directly to the cancer cell. And we are very honored actually, and we are proud that Professor Dhara was also sharing his pioneering work in polymer engineering, showcasing how the pH control with block polymers can effectively use the controlling drug delivery in cancer treatment. And with this, I am again thanked to Professor Dhara for sharing this insightful lecture with us. And this forum is open, so any participant have there any queries, share with us and you can ask.
Thank you, sir, for your wonderful lecture. Sir, if you don't mind, I have questions because right now one of my relative got cancer patient. Okay, so what I observed, she is under Apollo Hospital. She is going Monday to Friday to take radiations as well as chemo. So, and within 7 days interval, we do some blood test, CBC, creatinine, sodium potassium. What I observed that, so after going radiation and chemo, hemoglobin, amount of hemoglobin is falling down. So again, some fruits and other medicines they take. So why, when you use, when the chemo has been inserted, so why hemoglobin sir is falling down? So if you don't mind, so this is
But
what
my understanding again, this because these nanoparticle based drugs, drug delivery for cancers are very limited. There are only 1 or 2 products which probably are not marketed in India. I don't know exactly. But again, this is my understanding is the red blood cell is also cell. Okay. And so when you are injecting this chemotherapy drug in blood circulation, it can enter anywhere because drugs are free to, it has no mechanism to distinguish. Probably it will enter more because of the blood vessels are more leaky, more porous in cancer cell. It will enter more in the cancer cell or tissues, but it will also enter in these other cells, including red blood cell. And once it goes red blood cell, it will break the red blood cell and then release the, destroy the hemoglobin. And basically that's the reason probably. That is, that is my understanding to tell you, but that's it.
Okay, thank you, sir.
Probably Tina.
Sir, yes,
Yeah.
sir, I have one question. As you have said, this nanotechnology based the cancer medicine is probably still in the experimental level. It is
Yes.
not so much of use. So if when it will be coming to the market, will it be too costly?
They drugs are anyway costly. Probably, I don't think that probably cost will come down, because then you probably may require to use less amount of drug, because the lots of drug maybe you can save in terms of when you're using free drug, part of the drug is getting removed from the blood circulation using those normal mechanisms. So basically, and part of the drug is going inside the normal cells and doing the side effects. So basically, when you are using these nano systems, these nanoparticle polymers are not costly. Okay, the drug is mainly costly. So basically, if we can use this nanoparticle, I think the drug, the prices should come down. But prices, see, in this type of research, the prices is high because of the cost of research. See, the companies, when the actual cost may be less, but they sell these drugs in the market as a higher cost to recover their expenditures which they have spent during the entire research area. So they probably spending 10 years of research, and there's so much of money involved in that case. So they have to recover. These companies are there for making profit. They are not the social government companies where they're doing a free research. And so basically they will take the money out from the market. So they basically, this is not, cost is not because of the material itself, the drug itself, but the cost is because of their research, the expense they have made for their research for last many years. So that is the reason mainly, and they can use that money for future research as well.
Okay, sir. One more question. As you have mentioned in the beginning of your talk, that the oral chemo is not used because of its more side effect, as it enters or just interfere with the metabolism of the body. But there are lots of oral chemo. In fact, one of my relative has or is using that oral chemo like Cassette 500. So why the doctors are suggesting those oral chemo if they are so much harmful to the body?
So maybe they have taken, not all, maybe they are not, they have tested those drugs may be safe for the liver.
Okay,
See,
sir.
they will go through the this intestine and stomach, and then first they will go to the liver. And if they found that the drug has no effect, detrimental effect in the liver, so probably it is safe for the liver. So doctors may have found the data may have only in this. But there's also another thing, that some of the drug will anyway get lost in that if you take it orally. The bioavailability is always significantly less than 100% if you take orally. But maybe the drug is not that costly, or so doctor can afford to lose some of the drug. I don't know exactly.
Okay, sir. Thank you. Thank you very much for your nice informative talk.
Hello, sir.
Am I audible, sir?
Yes, you are.
So actually, you have shown a slide in which you have done an energy transfer study between DOCs and gold nanoparticles. So I would like to know that is that only the energy transfer which is acting as a mechanism between the DOCs and the gold nanoparticle, or there are some other like there is something like electron transfer or something happening in between?
No, it's an energy transfer.
Okay,
it is quite established.
Okay, sir. What about and sir, what about the images you have shown with the DOCs and nanoparticles? They are they confocal images, sir? And which microscope did you use to capture those images, sir?
No, they are confocal images. I
Yes,
don't remember the exact name of the instrument.
Okay, sir.
So pardon me for that.
That's
But they are
not
confocal images. Yes. Yeah.
Yes, okay, sir. Thank you, sir. Thank you.
Hello, sir.
Yes. Yeah.
Yeah.
Jivanand, sir. Yeah.
Yeah. Basically, the diabetes patients, they take an tablet like glycomat.
Okay.
Okay. In that, I have seen some glycomat SR, sustainable release.
Sustained release. Sustained
Yeah.
release.
Yeah.
Yes.
Yeah. Is it also based on coating a polymer over
Yes. Yes.
glycomat?
Yes.
Okay. Okay. May not be nanoparticle, maybe polymer they coat.
No, that is not nanoparticle, but the drug is entrapped in some polymer matrices. That
Okay.
matrix size is not a nano size polymer,
Okay.
but once they go inside your stomach and intestine, they get the polymer get. There are few mechanisms, different mechanisms, which I already also for the time I did not come through. There are different mechanisms by which first is your diffusion driven release, but if your polymer also helps in this case, if it is entrapped within the polymer matrix and the polymer, depending upon how polymer is getting degraded, your drug will come out. Then the rate determining step would be your polymer degradation rather than diffusion. So in that case, by controlling that polymer degradation or swelling, whatever mechanism they are using, by which they can control the release, or they can we slow down the release of the drug for a longer time. Okay. So
Okay.
maybe most of the sustained release are used for 8 to 10 hours or something like that.
Okay. Thank you, sir.
Any queries for participants? So it is so interesting, and it is very related to the daily life. So lots of queries from many people are there. So once again, if there is no other query, so I am once again from heartful congratulations and thank you, sir, for giving us this time and wonderful lecture. And this is the time now from our side. We want to give you a token of appreciation, digital memento. So
Sure.
I'm there, no problem. Please. Yeah.
and please, sir, accept this.
Oh, thank you for nice presentation, digital presentation.
And hopefully, because this is a so important field, and many people I think are working and wants to working on this field. So I think many of you are reach you for further discussion and collaboration and future work, sir.
Sure. Yeah. Always welcome here.
So thank you, sir. So we are very much grateful to you for your valuable time you spent. So it's a wonderful lecture, and we got a lot of information from you. Actually, this is very interesting. How does that working in our cell? This is very interesting.
Yeah, although it was not given the time, it was not possible. So I touched maybe a little bit.
Okay, sir. We
Thank
in
you.
future
Okay.
we will also arrange some type of talk also.
Okay. Thank you. Okay.
Okay, sir. Thank you, sir. Good night, sir.
I'll leave. Good night.
Yes,
Okay.
sir.
Good night.
Okay. Bye.